Hello, everyone. My name is Senqiang Song from Wuhan University of Science and Technology. So glad to present at a GTT users meeting. Today, I'm going to talk about recycling of chromium-containing waste oxide as alloying addition in ladle metallurgy, especially using FCG micros for kinetics modeling in the project. This project was done when I was at Carnegie Mellon University in Professor Chris Pistorius' group. To begin with, a little bit introduction about myself. I got a PhD degree in 2014 at Wuhan University of Science and Technology. And then I went to South Africa, University of Pretoria, did a postdoctoral with Professor Andre Haberts-Craig. And then in 2017, I went to Carnegie Mellon University with Professor Chris Pistorius. Now I'm working at Woost as an associate professor. Move on to today's topic. First, a little bit background. Second, the thermodynamic considerations. Third, the experiment. And then the kinetics modeling using FCG macros compared to the experimental results. Finally, the conclusions. This project is about to reuse a byproduct from another industry, which is a spent chromium catalyst from the petroleum engineering. It contains around 20% chromium oxide. The rest is mostly aluminum. Right now, this is a really difficult material to deal with in terms of handling after use. If one can actually utilize it in the ladle furnace, it is a way to both positively use this byproduct and avoid use the expensive ferrochromium. So the idea is in principle simple. It's just add this as a feeder into the ladle slag and let the reductant in steel like aluminum or silicon to reduce the chromium oxide and alloy the steel with chromium. And certainly thermodynamically it should work very well. For the aluminum kit, the steel reacts with chromium containing slag. We use the FCG to do the equilibrium calculations between the steel matte and the ladle slag. The target chromium in the steel is 0.1%. As we can see, the calculated equilibrium distribution coefficient of chromium between the slag and the steel are quite small, which means we can achieve a very high recovery of chromium. And also it means that the reduction kinetics is likely to be limited by the mass transfer in the slag. As we can see in the bottom, the effective mass transfer coefficient for a steel slag reaction can be simplified when the equilibrium distribution coefficient of chromium is small. And it's just related to the mass transfer in the slag. So far, for the whole kinetic process, we understand that with the equilibrium, the reduction reaction lies very much on the right side. And with low equilibrium distribution coefficient of chromium, it is expected that this reaction somewhere would be limited by mass transfer in the slag, not by the mass transfer in the steel. One potential concern is that if you charge too much chromium oxide into the slag, it might form the chromium spanner phase, which might slow down the dissolution of the chromium oxide. This is the straightforward calculations using FCG again. As you can see in the figure, it do indicate somewhere above 7% chromium oxide in the slag. One can expect the magnesium chromate spanner phase start forming. It can make up around 15% amount of the span phase in the slag if one can allow for that. So for the recycling of chromium catalyst in ladle metallurgy, if we target 0.1% chromium in steel, the initial chromium oxide charged into the slag should be about 10%. This probably means not charge the chromium oxide just in one go, or maybe in 2 batches. Another thing should be noted that the additional alumina would be introduced into the slag through the catalyst. So, additional calcium oxide and magnesium oxide would need to be added to maintain the double saturation of the slag. Laboratory experiment has been done in an induction furnace. The synthesized chromium slag contains 1% chromium oxide. It would expect to get 0.17 chromium in the steel if all the chromium oxide has been reduced out. This is the typical timeline for the 2 parallel experiment tests. Steel samples were taken to track the change of the chromium concentration in the steel mite, as well as the inclusion's evolution. Here are the measurements of the experiment. It shows the chromium has been rapidly reduced into the steel. I will show you the alumina and chromium concentration with timeline in graphics later. XRF analysis shows the final slag only contains 0.06 chromium or oxide, which confirmed that most chromium has been reduced into the metal. Move on to the kinetics modeling. Here we build a kinetic model of chromium reduction based on the effective equilibrium reaction zone model using Faraday microprocessing. The calculation procedure assumes the kinetics is limited by the mass transfer, and the local equilibrium can achieve at a slag-steel reaction interface. As you can see, a fraction of slag and a fraction of steel move to the slag-steel interface. After a local equilibrium, the oxides will move back to the box slag, where the metal will move back to the box steel. After that, the slag and steel compositions will be refreshed. So, firstly, let's look at the chromium pickup. These are the data points from the measurements of the 2 tests. 2 mass transfer coefficients were tested in the modeling. The coefficient of 3 times 10 to minus 4 liter per second did agree reasonably well with the experimental results, which means the chromium reduction was much faster than the desulfurization in our previous experiments. The break-up of the steel slag interface likely happened and increased the interface area during our chromium reduction experiment. The alumina concentration after slag being added was lower than we expected. This is because the powder slag introduced some iron and oxidized some aluminum in the mite. However, the rate and the extent of chromium reduction are not affected by the low initial aluminum concentration. The chromium reduction indeed is limited by mass transfer of the chromium oxide in the slag. A potential side effect is that the consumption of dissolved aluminum as a reductant here might change the evolution of the oxide inclusions, but the results showed that the inclusions chemistry change just follows the general sequence: aluminum oxide, spanner, and magnesium oxide, as we generally found in the aluminum kit still contacting with magnesium oxide in slag or refractory, so it should not be affected by the chromium reduction process. In conclusion, first, dissolved aluminum in steel can readily reduce chromium oxide from slag, which shows good kinetic conditions for recycling the chromium catalyst in nanometallurgy. Second, the inclusions in evolution in the steel was not affected by the reduction of the chromium oxide. Last but not at least, I would say phasaging micros, the chemipie I also use, are very useful to simulate the high temperature metallurgical processes. Thank you very much. Thank the organizer for such a good opportunity. I hope to see you in the near future.